Okay guys, let's go ahead and talk about the warm-up questions that are on my screen. Again, you should be answering these in My Open Math as well. So if you haven't yet done that, please make sure to make your way there. And then after we've gone over this, we are going to be taking some notes today. So hopefully you already have out some paper, but if not, you can go ahead and get that as we go over today's warm-up questions. So the first one says, will the pendulum continue to swing forever? Why or why not? And really, I probably should have reworded this because I don't mean this animated one. I mean one in the real world. If we set one up in this room and I were to release it, would it go forever? No. Okay, I heard a no over here. Why not?
Because of gravity pulling down.
Not because of that reason, though. Okay, it's not because of gravity. Gravity is what is going to make it. That gravitational pull is what makes it go down in the first place, but that's not why it stops. Friction, air resistance, things like that. Okay, and so it will eventually come to a stop. Because of those external forces that are acting on our pendulum. Okay, how could you keep it moving? If you wanted it to go, forever, how could you keep it moving?
Keep applying force to it?
Yeah, keep applying force to it. Push it. Like a kid on a swing that doesn't know how to make themselves move yet, you have to keep pushing them. Okay, and so same thing here. If you push it, or continue to push it, you could keep it going for as long as you're able to keep pushing it, okay, until you get tired. But theoretically, forever, if you had somebody swap in to keep pushing it. But you could keep it moving so long as you keep applying a force to it and thereby doing work on it. And that is going to be the topic of our notes for today. We're going to be taking notes on work and talking about that in 1 dimension and in 2 dimensions. You do have a homework assignment, however, it's not due tonight. If you look at that date, that's tomorrow. Okay, so you have an assignment that you can start today, which I would recommend because the first one is definitely the longest of the ones in the unit. In terms of the length of the assignment, I don't remember exactly how many questions it is, but I do know it's the longest one. So you might want to get a head start on it, but it's not due until tomorrow night. Like I said, you should have some time after we go over the notes today to get started on it as well. In addition, your bumper RA, again, this is from before Thanksgiving break, is due tomorrow. Okay, so hopefully you have already worked on that individual component of it. Maybe you're finished with it. Maybe you already turned it in. But if not, it is due tomorrow. So you need to make sure to open that thing back up and try to remember what you did so that you can complete that. In addition to the digital component you're doing by yourself, you also have a paper component that you're doing with your group. And that is the calculations. So you need to make sure to talk to your partner or your group about which calculations each person is doing. And if you're doing, the first 2, you can put those on a sheet of paper and the next person can do theirs on a different sheet of paper and y'all can just staple the pages together. Again, I want at least each person to work out at least one problem. For that, and y'all are welcome to work on that together as well, and some of you already did that whenever you were working before the break, but if not, then that is something that you also need to keep in mind, and maybe you can look at that whenever you're finished with the notes today as well. Did you have a question, Emily?
Of the calculations, you turn them in on paper?
Yeah, on paper.
And then the other, individual component, it's the poster online, right?
Yes. Okay, yeah, so I'll talk about it more at the end, but yeah. The digital, the individual piece of this is that digital, it says presentation or poster, and that is done individually and you submit it in Schoology.
Does it have to look nice? Or can it just be on a white piece of duck?
I mean, ideally it looks at least somewhat nice. But you can look at the rubric to see if I don't even remember if I put any points toward creativity or anything. But I mean, try to make it look presentable since it's supposed to be a poster. Okay, so let's go ahead and get into the notes for today. As I said, you are going to want paper out so you can jot some stuff down, starting with the topic of the unit, work. Okay, when a force acts upon an object to cause a displacement of the object, it is said that work is done on the object. I said that in the warm-up. I said we can do work on the pendulum by pushing it. Okay, if you apply a force to something causing displacement, you do work. There are 3 key ingredients to work. Okay, and I just mentioned 2 of them: force, displacement, and cause or opposition. We'll get into that a little bit more in a minute. But you have to have those things, okay? And we're going to go over different examples in today's notes. You're going to see different examples in the problem set for the unit. But you're going to see a lot of questions like who's doing more work or is this work? And these are the criteria you need to be mentally checking off in your head. Is there force being applied? Is that force, or is there displacement of the object, and did that force cause that displacement of the object, or is that force working against it, or is it not related to it at all? Okay. In order for a force to qualify as having done work on an object, there must be displacement, and the force must be parallel to the displacement. Okay, I underlined that must be parallel because that's going to be super important when we start looking at these examples, and I'm asking you, is this work? And you're going to look at it and you need to determine if any portion of that force is parallel to the displacement. And if it is, then you can say, yes, there's work being done on the object. If it's not, then you have to tell me no. Okay? So again, when a force acts upon an object to cause displacement of the object, it is said that work is done on the object. In order for a force to qualify as doing work, there must be displacement, and the force must be parallel to the displacement. Okay, when force applied to an object is in the same direction as the displacement, we would say that the work done on that object is positive. So if I push something to the right and it moves to the right, we would say that I did positive work on that object because my force is in the same direction as the object's displacement. The same is true if I push it to the left. I know typically we talk about the left as being negative, but if I push it to the left and it is displaced to the left, still an example of positive work. Okay, so if you are pushing or applying a force to an object and that force is in the same direction as the object's displacement, work is positive. On the other hand, if the force applied to the object is in the opposite direction as the object's displacement, the work is negative. Okay, what that would look like is if something is moving toward you, so let's say an object is moving to the right and you try to slow it down by pushing to the left. Okay, that displacement is to the right, but your force is to the left, your force is opposite. A more common example, everyday example, is friction. Friction can do work on objects as well. If I were to push the chair to slide it across the floor, and like let's say I push it forward, the force done by friction is always opposite the motion, so that force would be backward, and therefore it would be an example of negative work done on the object because the force is in the opposite direction as the object's displacement. Okay, when a force is applied at an angle, we've talked about things at an angle before. In fact, we talked about forces at an angle. Okay, so if a force is applied at an angle, only the component of the force that is parallel to the displacement of the object is responsible for doing work. And we're going to look at what that, it's going to be easier with a picture, I promise. Okay, but if you want to just jot it down for now, you can. Okay, but if you have a force at an angle, and we talked about this in our forces unit, if there's something at an angle, you have to find the horizontal and vertical components. Okay, and if there's a force applied at an angle, only the component, only that piece of the force that is parallel to the displacement is responsible for doing work. Okay, so again, we'll look at some examples of that. But if you have any component of your force that is perpendicular to the direction of the displacement, then that force will not be doing work on the object because it's not parallel. Okay, so again, we'll look at that with some examples. All right, so which man is doing work and why? There are 2 examples here. I want you to look at them. I want you to turn and talk to your neighbor, and I want you to look at your notes that you just jotted down for what constitutes work, and see if you can come up with an answer to this question. You have 23 seconds. Turn and talk. Okay, first guy, force without motion. Who thinks he's doing work? Raise your hand if you think that first guy's doing work. No? Why did you not raise your hand, Emily?
I have no clue.
Okay, anybody want to help her out? Yes, Nate?
Wait, just,
No?
I mean, I thought he was doing work, but then it said without motion,
Okay,
and so now I'm confused.
so now you're not sure?
Yeah.
What do you think, Mason?
No, because it hasn't moved.
Right. Okay, remember, there are 3 criteria. Look at your notes, hopefully they're there. Those 3 criteria say force, displacement, and cause or opposition. If he's not moving it, is there displacement? No. Okay, so although he's pushing it, and he could get very tired, it's probably a very heavy crate, looks really big. Doesn't matter. He's not doing work if he doesn't cause displacement of the crate. So the first guy not doing work. What about the second guy? Is he doing work?
No.
Why do you say no, Vivi?
Because the force is parallel.
Because the force is not parallel to the direction of his displacement. He is not doing work. If you are simply carrying an object, doesn't matter what the object is. If I get up and I carry this notepad across the room like this, the direction of my force is upward. I'm supporting the weight of this object. And yet, if I'm walking forward, my displacement, or this object's displacement, is in that direction. Now, lifting it, this is work. Okay, actually lifting it is work, because then the force is parallel to the displacement. But in this example, carrying a box like that, and again, you'll get tired, but that's not how we define work in physics, okay? So, kind of a trick question, because the answer is neither of them, okay? Neither of them is doing more work, because neither of them is doing any work at all. And that's what I mean whenever I say you're going to get questions like that, and they may be like this: who's doing more work? And the answer is nobody. Okay, so please be careful and make sure you understand those criteria. So hopefully they're on your paper. If they're not, add them. You can even write down these examples and write why they're not work, because you'll probably see them again. Pretty common example, especially the second one. You'll see quite a bit in questions. Okay, so again, neither of these men is doing work on the box, because neither of them has force causing displacement where that force is parallel to the displacement. He doesn't have any displacement, and of course his force is perpendicular. All right, so again, here's a kind of better definition, because we didn't really write a definition so much as just a few sentences about work. If we were to define it, we could define work as a measure of energy transfer that occurs when an object is moved over a distance by an external force applied parallel to the direction of the displacement. So again, it has the same criteria in the definition. We have to have displacement, meaning you have to have some distance that has been traveled, and the force must be parallel to the displacement. The equation that we're going to use for work is on my screen right there, and it is work, or W, capital W, equals F times D times cosine of the angle theta. Okay, force times that distance that you've caused it to move times cosine of the angle. And again, if there isn't an angle, then it's cosine of 0. Do you guys know what cosine of 0 is off the top of your head? 1. Which means that it just becomes force times displacement, okay, if it's not at an angle. Okay, but if it is at an angle, you'll have to take that into account, and that's what I was mentioning earlier. Okay, the units for work, the unit we use is joules. It's a capital J. But I did want to put up here that another unit that you could see, and really one that you probably saw more in chemistry when you were talking about energy, because work is energy transfer, it does use the same units as energy, is calories. Now, we don't use calories in our calculations, but just so you're aware, because again, you saw it in chemistry, or you should have. Calories is also an acceptable unit for work. It's just not the standard one that we're going to use in our calculations. Okay, so again, work. Measure of energy transfer that occurs when an object is moved over a distance by an external force applied parallel to the direction of the displacement. All right, so here it is again. Is it work? I have 4 different images up here. You can see the direction of the force. It's labeled with the black vector. You can see the direction of the motion or the velocity of the object. It's labeled with the gray vector. There are 4 here, A, B, C, D. So take a moment to look at each of them. Check those criteria that you have written down. Turn and talk to your neighbor. And I want you to tell me which one or which ones are doing work. You have 29 seconds to discuss. All right, Brayden, which one did you say is doing work? You can tell me just one of them, or if you have more than one, you can tell me more than one. A and B. Anybody else doing work, C or D? No, that's like the previous 2 examples I just showed you. But both A and B represent somebody doing work on this crate. For A, it's obvious those are definitely parallel. Okay, the force and the displacement are parallel. For B, that's the one where I said if the force is at an angle, if any part of that force is parallel, then that portion of the force would be responsible for doing work. In this particular case, because he's pulling at an angle, he's pulling both up and to the right. Now, the portion that he's using to pull up, not doing work because it's perpendicular. But the portion, the component of his force that is applied horizontally, this piece here, if we were to find the components, that would be responsible for doing work. And of course, we would have to do some trigonometry to figure out what that component is in order to do our calculation. Okay, but if you have it at an angle and if it's at an angle, okay, any portion of it is parallel, then you can say that work is being done. Okay, so those 2 are yes, those 2 are no. All right, and I mentioned this already, but lifting a box from the ground is work. Okay, now he's not lifting it here, he's carrying it. But if I was to show you an example of him lifting it up, that would be work. Anytime you lift an object upward, you do work against gravity to lift the weight of that object. However, holding the box or carrying it and walking forward is not work. Okay, the force must be parallel to the direction of motion. So what's shown here is not work, but again, if we were lifting it upward or even lowering it back down, okay, then we could say that work was being done on the box. Okay, you'd be working against gravity as you lift it upward. Okay, but here he's just carrying it, and yes, he will get tired, especially if it's heavy, but not going to be work because his force is perpendicular to his displacement. Again, these 2 were both doing work. I have a little follow-up question here. If both boxes are identical, and each box moves 5 meters across the floor, and both men exert 300 newtons of force. So this force vector represents 300 newtons, and this force vector represents 300 newtons. Who is doing more work? Or is it the same? What do y'all think? I'll give you a moment to talk about it since you seem unsure. It's early. You have 19 seconds. Who's doing more work? Turn and talk to your neighbor. All right, does anybody think they know? What do you think, Skylar? The top one. The top one is doing more work. Because if you pull something at an angle, only a part of your force, something less than 300, we could figure out how much if we did the trig, but it's less than 300. Okay, and so he has less force that is in the same direction as displacement, and therefore he will be doing less work, okay, than this guy up here whose force is completely parallel. All 300 newtons are responsible for doing work. Down here, only a part of it is. Okay, so you'll see questions like that where you don't necessarily have to do the math, although you could if you wanted to figure out how much more work. But you should be able to answer that conceptually. And again, here's why. All of his force is parallel to displacement. Only part of his force is. This component right here would be, but it's going to be less than 300. We know that just because of what we know about triangles. Okay, the hypotenuse is going to be the longest of those sides. And so I know if this hypotenuse is 300, this is something less than that. And yes, you could calculate it because they gave you an angle. But we're not going to worry about that just yet. All right, but again, force must be parallel to the displacement for work to be done, so only this piece is doing work. Okay, but if you have more force that's in that parallel direction, you have more work being done. All right, so let's put some numbers to it. Okay, so for this guy up here, again, in the question it says that they caused it to move 5 meters. His force is 300. If I wanted to find his work, pretty easy, 300 times 5. Which is 1,500 joules. Okay, that one's pretty straightforward. If we want to figure out how much work this guy at the bottom is doing, okay, you could find out what this component is. Because it is adjacent to my angle, I could use cosine, SOHCAHTOA, right? Cosine of my angle theta, in this case 30 degrees, is equal to the adjacent side, that's my green vector, okay, divided by the hypotenuse, that's 300. Okay, and so if I rearrange it, I get this, 300 times cosine 30. Okay, or I can just go directly to the equation that I wrote on our notes, FD cosine theta. Well, guess what? That's the same thing. Here's that 300 times cosine 30 again. That gives me the piece that's responsible for work, and then I multiply it by the displacement. Okay, so that piece times 5. Okay, so 300 times 5 times cosine 30 degrees. If you're doing this calculation along with me, please make sure that your calculator is in degree mode. Otherwise, you will not get the correct answer, which should be 1,299 joules. So again, we can prove it mathematically as well. He is doing less work because only a portion of his force is in a parallel direction to his displacement. Questions about this? All right. This is another important note for you to write down. And you can just write down, you can write down more than just this, but the title of this slide. Work is independent of the path taken. This is another type of question that you will see over and over again. Okay, not just who's doing more work, but also things like this. Okay, work is independent of the path taken. If you look at my diagram here, I have two people, a boy and a girl, that are both lifting some kind of box up to the top of a ramp. And we're going to assume that they both started at the ground and that they're both lifting it to the same height, however tall this ramp is. Okay, and if I asked you who does more work, okay, your answer is going to be that they're the same. Okay, they're going to be the same because they're both doing work against gravity. Okay, because they're both lifting this object against the Earth's gravitational field, and they're both lifting it to the same height. So it doesn't matter how they get there. Okay, work is independent of the path taken. That's what that means. It doesn't matter how they get there. If they started at the same location and they ended at the same location, okay, you're going to have the same amount of work being done. So the same amount of work is done to lift a box as it takes to push it up a ramp to the same position, ignoring any friction. Of course, if we add that in, it's a little bit different. Okay, so the force each person must work against is acting down toward the center of the Earth. It's the weight of that object. They're both working against gravity. Okay, and the vertical displacement, the height that they are transporting this box to, is equal. So again, assuming they both started on the ground, let's say that this ramp that they're lifting it to is 2 meters high. Okay, well, they're both going to have a total vertical displacement of 2 meters, and they're both working against gravity, and so they're both going to have done the same amount of work. Okay, now her job is a little easier because she can use less force over a longer distance than he can. Okay, but at the end of the day, they're both going to have done the same amount of work in getting that box up to the top of the ramp. Okay, so again, if you want to write down these words right here, work is independent of the path taken. You're going to see that again over and over again because you'll see questions like this, who's doing more work, and your answer should be they're the same. Okay, so the same amount of work is done to lift it as it is to push it up a ramp to the same position. Again, assuming we started at the same spot and we end at the same spot, and ignoring any friction. Okay, while both methods require the same amount of work, lifting the box requires greater force applied over a shorter distance. Okay, I mentioned this a second ago. Hers is an easier task because hers, pushing it up the ramp, takes less force, but it must be applied through a greater distance. She's got to push it a greater distance, but she doesn't have to use quite as much force to do it. But at the end of the day, she's going to do the same amount of work that he is. This, by the way, is how many simple machines work. An incline plane is an example of a simple machine. You guys, I think, still learn about simple machines in junior high. Yes, maybe? I don't know. We can talk about that later. But they trade off the force required for the distance through which it is applied, or vice versa. So it can require less force, but take a greater distance to do it. Okay, and an incline plane or a ramp is an example of something that allows you to have that trade-off. You'll do the same amount of work at the end of the day. All right, when is work zero? So here we have an animation of a guy lifting a box and then carrying it and setting it down on this countertop. And so I've broken the portions of his motion into 4 parts. The first one says the man accelerates the box upward from rest for about 0.1 meters. Once he gets it moving upward, he then continues to lift, now at a constant velocity, and then he carries it while walking forward, and then he accelerates it downward to bring it to rest on a counter. Okay, so he drops it back down. Okay, and so if we look at when work is zero, again, we're looking at the same criteria we've been looking at the whole time. What does it take? What is required for work to be done? Okay, so again, lifting, we talked about this already, lifting is work. So A would be work because he's lifting. B, once he gets it moving upward, he continues to lift, still lifting. Doesn't matter if it's constant velocity or if it's accelerating, the man would be doing work here. Now, if it is constant velocity, okay, it's a little bit trickier because if we're talking about net work, which you're going to see in the assignment that you have in my open math. Okay, but he's going to be doing work anytime he's lifting it, if we're talking about what the man is doing. But when he carries it while walking forward, not work. Okay, when he accelerates it back down, work. It's again parallel. Okay, so he's doing work except for the part where he's carrying it, the man is doing work. We can also graph this. Okay, so here's a graph of the motion I just showed you. Okay, he applies that upward force to accelerate it, and then he is applying that force to lift it at constant velocity, and then he is putting it back down again. Okay, and so again, you don't have to be able to graph that, but I do want to talk about this. When you have a graph that plots force against displacement, okay, you can use that graph to get work, because work is force times displacement. Anytime you multiply your x and y axes, which is what you're doing here, x times y, because that's force times displacement, you find the area. The area of a force displacement graph tells you work. If you want to write that down, you can, because you're going to see questions like that. The area of a force displacement graph is going to tell you how much work is done. Okay, so the area under the curve, and I know this isn't a curve, it's nice and boxy because it's easier for us to find area, but the area under this line that's shaded here is going to represent the amount of work done by this guy. Okay, so if I asked you to calculate how much work that is, you would want to break it into regular shapes, which would look something like this. Okay, so you have this green rectangle, this big yellow one, and this smaller purple one, and you could find the area. Okay, so it says the FD graph shows data for lifting a 1 kilogram box to a height of 1 meter. Again, if we wanted to figure out how much work that is, we can find the area. Okay, so area is work. So for that first green portion, or teal, whatever color that is, I have my force times displacement. So my displacement here is 0.1. My force here is 12. Multiply that. That has an area of 1.2 joules. So for the first 0.1 meters of lifting, he has done 1.2 joules of work. For the next portion of the graph, from 0.1 to 0.9, that's 0.8. Okay, the displacement there is 0.8. And the amount of force there is 10. Again, I'm just reading the numbers from the axes. 0.8 times 10 is 8. And then the last little bit, his force is only 8 newtons, and this is going to be for 0.1 meters. So 0.1 times 8 is 0.8, and I could add them all together to get my total work of 10 joules. So again, if I give you a graph and I ask you how much work is done in this whole graph, you find the whole area. If I asked you how much work is done for the first 0.5 meters, you would just find the area of that portion of it. So make sure that you read it carefully and find the area for the portion you're being asked about. All right, here's another graph, and it says a horizontal force pulls an object across a horizontal floor. The graph at the right describes the force and displacement. Find the work done on the object in the graph. So again, same thing. We're going to find the area. If you have a force displacement graph, find area. So we're going to break it into regular shapes. We have this triangle. Okay, triangle 1/2 base times height. We're going to assume that these numbers line up really nicely. And so I'm going to say that that's 1/2 times 1 times 10, which of course is 5. Okay, then I have a rectangle from 1 to 3. That's going to be length times width for rectangle, 2 times 10. Because again, from 1 to 3 is 2, and then this is at 10. 2 times 10, of course, is 20. And then this last one is not quite a regular shape, so we need to break it in half. We have a basically triangle sitting on top of a rectangle. Okay, so there's my triangle. Let's find that area first. The base of it from 3 to 4 is 1. The height of it from 10 to 30 is 20. So 1/2 1 times 20 is 10. And then we have this yellow rectangle underneath. Length times width, 1 times 10 is 10. So if I asked you to find the work done, you simply add all of those numbers together. 5 plus 20 plus 10 plus 10 is going to give me 45 joules. Okay, so if I give you a force displacement graph, just find the area. Questions about the graph? Okay. All right, guys, then for the rest of the class period, you can work on either your bumper RA if you have not yet finished it. It's due tomorrow. You need to turn in both a digital poster in Schoology, and that's one per person. That's not for your whole group. And then secondly, paper calculations, but that's one set of calculations per group, and hopefully you all have already divided up the work for that. But if not, why don't you pull that back out and make sure you know what you're doing and what they're doing. There is also a video on the next slide from Crash Course Physics that kind of gives you a quick preview of the whole unit, and you're welcome to watch that. And then the last thing is, of course, your My Open Math assignment, but it's not due tonight, it's due tomorrow night, 601.1 work problem set. Okay, so if you have any questions for me, please let me know. Otherwise, I'm going to let you guys get to work.